All right, well, that's not all visible online while drawing a thicker pen when I actually draw the answers, but you can get your practice exam out. And today what we'll do is review. These are the first few problems you see here from the practice set that's on Canvas under the Files tab. That's where all of my stuff is. I don't fill it up with all sorts of other things, just handouts. So if there's any problems you want to look at in particular, we'll look at those. Otherwise, I can pick some of these and go through them. The problems on the exam Monday are going to be similar to homework problems, most of them similar to these practice problems, but not all of them. People have been asking me, are there going to be this many problems? No, of course not. It's way too long. It's a 45-minute test. I can't make it much longer than that, right? Because it'll run in somebody's previous class or somebody's class afterwards, or so we're going to have a very short test. I'm really sorry for this semester. I feel awful having to present things this way, but that has to include, you have to download it, right, print it out, write in your test, and scan it or photograph it and upload it. I'm going to send the test out by email on Monday, so don't show up for class, right? Be by your computer somewhere or a computer somewhere so you can download this and look at it. If you don't have a printer, some students don't, especially you get foreign students, I'm always surprised. They get all this money to go overseas and pay out-of-state tuition and everything, and they don't give them any money for books or computer or anything else, and they don't have a printer or whatever, and they're handicapped in their classes. So if you have that problem, you can just look on your iPad or your cell phone or whatever and write it on blank pieces of paper. Put your name at the top. It's always frustrating. I print these things off, and I don't know what email they came from anymore, and I have to look through all the emails to find your exam, so put your name on it. And you can scan it to me and send it back, or you can photograph it and send it back. If you have technical difficulties, I understand it's the first test, just tell me, I can't print, or whatever. But you have to be able to look at it and write it out and send it back by email. It's open book and open notes, right? Use whatever resources you want like that, whatever calculator, but nobody can help you. No person can help you, no tutors and so forth. So it'll be in that vein. I'll send it out, write it at the beginning of class time, and then you have 45 minutes to do it and get it back. Any questions on the exam then? It's on, I should say again, it's on chapter, what is it, 13? The one we just finished. 12, okay. 12, yeah, chapter 12, and the section on conic sections, which I think is 11.5. So chapter 12 plus the supporting section on conic sections from 11.5. And this gives you a pretty good smattering of problems out of there, so you have a good idea. I won't do anything on vector calculus out of chapter 13 that we just did this week. Any other questions on all this? All right, well, with that in mind, then let's do some of these review problems. They can be off this practice test, or they can be something else. If you have a question on some of the homework or whatever, we can do that too. I just put this up for convenience. These are the first few. They're not necessarily the hardest. I have some of these written up, but not most of them. The answers are on the back page. You can go back and check if you did it right. If you come to meet me at my office hours or whatever, then, or you can't meet my office hours. I guess I don't have any today, but if you want to meet for office hours, send me an email, say help, and I'll try and meet you some other time. I have another student I'm already meeting later today. Just make sure you go to my address on the syllabus that's for the office hours, not the one that's for the class. Right? I have a separate office hour Zoom address than for the lecture address. And it's on the syllabus, and the syllabus is on Canvas. If you forget what it is, you can just go there and click on it. Actually, click on the PDF there. I've got a bunch of the videos. I've got all but the first two videos on there. The first two I have, but they're so bad I didn't think you'd want to see them. This thing is buzzing, and you can't. It's crooked. And anyway, so I hope it's better now. You can go back and look at the lectures throughout the semester. If you just go to Canvas again and under Files, find the one that says All Video Lectures or something like that. That's a PDF. If you click on the link there, it will just take you, unless you've got some program to block it, to the lecture on YouTube, and you can watch the lecture again if that helps you. I know it's only 1 weekend to fill the test, but the lectures are up there, the notes are up there, except that the first two lectures aren't the videotapes I didn't bother to put up. All right, I hope I didn't take too long with that. Anything in particular that's been giving trouble that you want to look at? I guess it's all easy. Okay. Let me look at 4B just for fun, man. That's one of the harder ones, I think. I think these are not extremely hard because the calculus isn't coming in yet. But if you didn't do vectors before, didn't do a little bit of other science before, it's harder than if you did. A lot of people have seen more of this before than others, unfortunately. But the rest of the semester will be calculus of these functions of more than one variable and of vectors. Here's an interesting problem, is number 4, 4B. If we move this up a little, is this hanging weight problem. It is. Says find the tension in each cord for the hanging mass. You've got 2 cords hanging down and a mass of 100 pounds. Pounds is a force, by the way, not a mass. So it's mass times gravity, actually. It's so many slugs times 32 feet per second squared acceleration gives mass times acceleration is the force of 100 pounds. So what I did for this problem, I'm going to have to zoom this out a little bit now so I can see the notes. As I said, here's the ceiling. Here's the mass. I'll just treat it as a point mass, maybe at the center of the block there. And it's pushing down with 100 pounds of force like that. So I'll call it FG, this vector straight down. It has length 100 pounds and it has direction straight down. Then a tension is actually the force in the cord, the force with which the cord is pulling. And so there's a tension in this cord at 45 degrees from the picture, and we'll call that T2. And there's a tension in this cord pulling it back this way at 30 degrees from horizontal, and we'll call that vector T1. So there's a vector T1, a vector T2, and a vector FG for force of gravity, whose sum is equal to 0 because the mass is in equilibrium, right? It's not moving. If it's not moving, then it's got 0 acceleration. So the net force, adding those 3 together, is 0. We got a little physics problem here. But the object is that, physics and engineering, those kind of things are the people that use vectors the most. You use them in other places too, of course, but they use them a lot. And this is a basic concept that if things not accelerating, such as so it's moving in a straight line velocity or it's just not moving at all, then the sum of the force vectors is 0. So having that equation now, I can actually solve for what are T1, T2, and the force of gravity. And here's what you can do. Get this out of here, sorry. The force of gravity being straight down at 100 pounds has components 0 minus 100. We'll call y the vertically up direction. So it's 0 minus 100. Is this vector right here, just because I know its length and direction. Then this vector T1, I drew over on the side here, here's T1, this vector, and it's at 30 degrees from the horizontal up here, right? Here's horizontal, 30 degrees down. Here's a parallel line here, so alternate interior angles makes this 30 degrees also inside this vector here. And now I can say that the 30-degree angle and hypotenuse length of T1, by trigonometry, this is length of T1 cosine 30 degrees, this is length of T1 sine 30 degrees. So you might see this in your first year physics class if you take that class. But you just hypotenuse cosine angle, hypotenuse sine angle on any right triangle. And so now I can find the components of this because 30 degrees is a special angle. This makes, I guess let's write it in here. And then the other triangle is at 45 degrees from vertical, and so by alternate interior angles, this is 45 degrees if I draw this little box here. Here's T2. It's hard to read. I have to draw this big, thick pin, and it doesn't fit very well. So that's length of T2, that says. At 45 degrees, that says. I hope I don't have to interpret everything here. And so this is length of T2 cosine 45 degrees. This one is length of T2 sine 45 degrees. I'm sorry that's so hard to read. Any thinner and you can't see it online. And now you say that the sum of the vectors is 0 becomes, here's the force of gravity, 0 minus 100, plus this one, T1 cosine 30 degrees, T1 sine 30 degrees, plus this one, T2 cosine 45, T2 sine 45, equals the zero vector for the total acceleration. Right? Any questions on that? That's maybe the hard part is setting it up. It's just trying to write these vectors, but that's exactly how you use them in practice. I told you before, I think I worked in aerospace for a while. This is, well, you get these kind of vector problems all the time there. So, all right. With that in mind, then, we can say, well, I know these angles, they're special angles. Cosine of 30 degrees is square root 3 over 2. You just draw the 30, 60, 90 triangle. But it's negative, right, because it's in the minus x direction. If you see the picture up there, right, it's this one. So it's minus square root 3 over 2 and plus 1/2, or the size of this triangle, because you went left and up. So we'll call this minus square root 3 over 2 length of t1, and sine of 30 degrees is 1/2 multiplies length of t1. And here, cosine 45 degrees and sine 45 degrees here. Both those components, they're right and up. So they're both positive. And the sum of those three vectors is the zero vector, the vector with all components 0. And then two vectors are equal. The left and the right are equal if and only if they have the same components, right? So 0 on the right here, the first component of the zero vector has to equal the sum of the x components here. 0 plus this one is, right, 0 equals minus square root 3 over 2 length of t1 plus square root 2 over 2 length of t2. That's equating the first components in this equation. Then you equate the second components. Minus 100 plus 1/2 t1 plus square root 2 over 2 t2 has to add up to the 100. Has to add up to 100 the other way. I took this minus 100 and put it on the other side where it's 0. So it's actually plus 100 now equals the sum of these. Right, if I add 100 over to this side and then switch sides. And so you have these two equations for two unknowns, length of t1 and length of t2. Now you just have an algebra problem, right? Two equations and two unknowns. You can solve for one in terms of the other and substitute it into the other equation. That works. What's usually easiest, if you call those equations number 1 and 2, is to add a multiple of one equation to another to eliminate a variable. And I say you can do either way here, and they both work pretty well. If you have more than two equations, substituting from one into the other starts to get very tedious. If you have more than 3 equations, it's just always making a mistake doing that is what it amounts to. So we'll do like they do in linear algebra and add multiples of equations to one equation to another, called the elimination method. And maybe you've heard it if you took linear algebra, Gaussian elimination. That's a particular orderly algorithm to do this that always works. But elimination in general works. You just have to pick an appropriate order. So we'll add, to eliminate these, there's lots of ways we could do it. We could take equation 1 and subtract equation 2. That would eliminate T2. Or we could take, let's see, what did I do here? Did I do this wrong? No. I did this wrong. I wonder how. I can take square root 3 times equation 2 and add it to equation 1, right? If I take square root 3 times this and add it to this, these will cancel. Let me rewrite that there. It looks like I got sloppy. I always tell people on here, check your answers. The really top students almost always do, because everybody makes a dumb mistake somewhere in the test, especially in a rush. Let's call those the two equations, and I'll try rewriting this. Now, I didn't check that's the answer in the back. The answers in the back have been pretty well checked. I think they're all right. So if I take square root 3 times equation 2 and add it up to equation 1, all right, then square root 3 over 2 here plus minus square root 3 over 2 will add up to nothing. Square root 3 over 2 times 100 is added to 0 here. Square root 3 over 2 times this one to this one adds to 0. And then square root 3 over 2 times this one added to this one gives me square root 3 times this is square root 6 over 2. That's square root 3 times this one added to this one, square root 2 over 2, all times length of T2. That's what you do. Take that, do that. Or you can just subtract the 2, and that works also. Maybe I should do it that way since I'm reworking it. That's even easier, isn't it? Let's just do that. I mean, this works, nothing wrong with it, but it's harder numbers, let's make it easy. So let's take equation 2 and subtract equation 1. Let's do that. Then the T2's cancel, right? This one minus this one adds to nothing. This one minus this one makes 1/2 minus a minus square root 3 over 2 all times T1. Right? So this square root 3 times this one, or yeah, square root 3 times this one added to this one, and then square root 3 times this one. Oops, no, I'm sorry, subtracting. This one minus this one gets this. And then 100 minus 0 gives 100. So you get that equation by taking equation 2 minus equation 1. Now, let's see, that's 1 plus square root 3 all over 2 times T1 length equals 100. And now you multiply by the reciprocal here and get length of T1 equals 200 over 1 plus square root 3. So there's that one. Now that's the length of T1. Now I can plug that into either equation and get the length of T2. I don't know which one's easier. Maybe the first one, since it doesn't have 100 on the right. Put this into equation 1, and then you got minus square root 3 over 2 times this one. 200 over 1 plus square root 3. So that's minus square root 3 over 2 times what we just got, plus square root 2 over 2, length of T2 equals 0, the right-hand side. And then that tells you what T2 is, a little algebra. So you apply algebra in the room here. Let's put this in here. Then you just say apply algebra. Out of room on that page. There we go. Sorry about that. Any questions on that one? I think there's some engineering students in here, isn't there? Yeah, several of it. I'll show you just for fun something else you can do with this. The whole purpose of this problem is to teach you vectors, and that's the vector way to do it, which is really nice. I want you to pick up the vectors. But there is actually this additional way to do it called Lamy's law. And you can also solve it this way. If you have 3 forces, exactly 3 in equilibrium, you can also do this. If you got force 1 here, force 2 here, and force 3 here, and these are the lengths of the forces I wrote. I didn't draw the vector on them because they're the lengths. And they have opposite angles, alpha opposite F1, beta opposite F2, and gamma opposite F3. Then you write down what looks like it's identical to the law of sines for a triangle where you have a side and an opposite angle. If sine alpha over its opposite force equals sine beta over its opposite force equals sine gamma over its opposite force. You can actually solve this problem a lot faster this way. This is a theorem that they use in engineering. It avoids all those vectors. So I'll say this is a good way to check your answer, but I'd like to see the vectors on the test if I give you that problem. Right? But this is easy to memorize because it's the law of sines. If these were triangle sides instead of vectors. Same form of the law of sines. Okay, does that warm me up to any questions that you're having on the getting ready? Keep this one. I'll try to put the notes online again if you want to catch up on those. Well, but surely people have a lot of questions. Everybody got their differential equations test this week, right? Here's a good simple question. Suppose I asked you to do 9A. One of the things I want you to be aware of is that I said these things would be like the homework problems and the practice test problems. Some of the practice test problems are not quite like the homework. Here's, well, some of them I ask you to do a sketch. Online, when you do the homework, it just says which one would be the answer if they can't make you sketch. But on the test, I'm going to ask you to sketch these things, quite possibly. So be able to actually draw the picture yourself for some of these. You know what the ellipse looks like and the hyperbola and so forth. This first one just says, find the vertices foci and center. I'm going to recommend always finding the center first. Of the ellipse, I gave you a hint there, whose equation is x minus 1 over 4 squared plus y over 9 squared equals 1. So what's the center of that thing? Right off just by inspection. Put you to sleep. Yeah, it's just whatever's subtracted from x and y. So x minus x0 over a squared plus y minus y0 over b squared equals 1 is an ellipse centered at x0, y0. So it's 1, 0, just what's subtracted from x and what's subtracted from y. It's whatever's subtracted, not what's added. So there's the center. And now, how can I find the foci and the vertices? Well, I can see something immediately, right? Whatever's squared on the bottom here and whatever's squared on the bottom here are a and b, but the largest one is a. So a equals 9, the larger of the two squared denominators, and b equals 4, the number that's squared over here, again by inspection. We could say by inspection, all these things come out. And you also notice that the ellipse is oriented vertically. So the foci are vertical, I mean along a vertical line, because the larger number A is under Y instead of under B here. So if the foci are vertical, they're on the line that goes through the center, then where are they? Well, it's hard to tell, and it's also be the major axis is vertical. So if we want to find the vertices, you can just go from the center, 1, 0. Oops, I wrote this in the wrong order. Make that 1, 0, and in the vertical direction go plus or minus a, so plus or minus 9. So the vertices are actually at 1 plus or minus 9. I just go up and down a units to get to the ends of the ellipse. And then they also tend to call the vertices at the end of the minor axis, so that we also say go in the x direction 1 plus or minus 4. And so these are the other vertices at the other end of the ellipse. And what we're drawing is an ellipse that, or if we sketch this, I didn't say sketch on this part, but I might on the test. I asked you that on one of these other problems here somewhere. Lost it. There it is. I guess I didn't on that problem, but I might ask you to sketch this in the test. That's part of the learning process here. So you go over to the center, 1, 0, which is right here. Okay. And then you go plus or minus 4 in the x direction to 5, 0. That's a point. And minus 3 on the x-axis here. And then you go to 1 plus or minus 9. So you go up 9 units. 1, 9, and down 9 units. 1 minus 9. And then you draw an oval shape. Like that, and there's the vertices. Now, how do I find the, and you can do this if you want, don't have to do this. This is just show you where the axes are. How How do I find the foci? Yeah, remember for the ellipse and the hyperbola, it's different. But for the ellipse, a squared equals b squared plus c squared. For the hyperbola, it's c squared equals a squared plus b squared. But that means for the ellipse, I can say, well, then c squared, he's right, is a squared minus b squared. And c must be square root of a squared minus b squared. C has to be positive. And so it's square root of 9 squared minus 4 squared is square root of 20, or 2 square root of 5. That means, now here's where I like drawing the ellipse. You don't have to draw it, but when I draw it, I recognize immediately the foci are vertical because the major axis goes vertically. And I just go from this point up square root 5, 2 square root 5. So this is 1, 2 square root 5 is this one, and go down 2 square root 5, and I get down here and I get 1 minus 2 square root 5, and those are the foci. Focus, focus. Place where you could sit in the whispering gallery, for instance, and hear each other. All right, so that's what I wanted on that one.
How do you get 2 square roots of 5?
Oh, I did real fast. I did it wrong, didn't I? Yeah, I was thinking 36 minus 16 is 20. And this is why you check your answers again. 81 minus 16 leaves me 75, right? No, 65. And so it should have been square root 85. Well, there's nothing that comes out of there, does there? So I guess it's just square root 85. 65. See, until I didn't get enough sleep. I was out getting groceries till 3 in the morning. Square root of 65. And so this, you're right, this should be 1 square root of 65. Thank you. I'll put this online with a recording wrong otherwise. You'll get it wrong on the test. You get it wrong on the test, it's still your fault. All right. Any other comments? All right. Motivate any more other problems you want to look at yet?
You do 10A.
Okay. No, I don't know. Let's just try to pick that one. Okay. Good. All right, let's try that one. 10A. Sketch the points described in spherical coordinates by rho less than or equal to 1, 0 less than or equal to theta less than or equal to pi over 2, and pi over 2 less than or equal to phi less than or equal to pi. On the homework problems, they just said identify it. I'm going to say sketch it. Well, what is this? What is rho less than or equal to 1? What's the sketch of that by itself? Rho is the distance from the origin, right, in spherical coordinates. So this is all points less than or equal to 1 unit from the origin. It's the unit ball. In mathematics, we always have to be absolutely perfect, right? Once you make a mistake, it propagates, and you can show that the moon is made of green cheese or something. Once you assume a mistake. So the unit sphere is rho equals 1. That's all the points at distance 1 from the origin. When we want less than or equal to 1, the sphere with its interior, we call it the unit ball. The closed ball to be specific. Otherwise, you leave out, if it's open ball, you leave out the sphere itself. So this is the unit ball, closed unit ball, at the origin. 0, 0, 0 in spherical in 3 dimensions. And then what is this? Theta between 0 and pi over 2. We didn't get to do enough of these in class, did we? We're kind of rushed with that 5-minute loss every time. What does it mean for theta to be between 0 and pi over 2? Think what it means for theta to be equal to constant. If I put theta equals 0, that's all points. Here's theta equals 0 in the xy plane, right? The xy is this ray out along the x-axis, right? And theta equals pi over 2 is this ray out along the y-axis. And now I'm going to let R be anything. I can go out any length of row, excuse me, any length. And I can also let phi, well, let's just, if I let rho and phi be arbitrary, then I get this half plane here going out on the y-axis and this half plane here going along the x-axis. And what you get is quadrants 1 and 5, octants 1 and 5 in three-dimensional space. So you're going between these two things. This looks like one of those dressing things. It's got two sides to it, and you're between the two shutters there. You're in octants 1 and 5 by this restriction. Now, what's this one? Phi equals a constant is a cone, right, in general, although phi equals pi over 2 that I put here is the exception. Phi equals pi over 2 means you come down pi over 2 to the xy plane, and then you have arbitrary rho and theta, and so this is actually just the xy coordinate plane. Phi equals pi over 2. Doesn't look like pi over 2. Pi over 2 is the xy plane. And then phi between pi over 2 and pi means that you're actually below the xy plane in octants 5, 6, 7, or 8. So that's what phi bigger than or equal to pi over 2. It gives you everything below the xy plane, those 4 octants. Theta between 0 and pi over 2 gives you the 2 octants 1 and 5. And now the intersection, what you want is all 3 of these to be pulled at the same time, right? What this really means is the intersection of these 3 sets. And so what's in both these sets is just octant 5, right? Octant 1 is over here, and these other octants aren't here. So between these, we just get octant 5. And now we have what's in the unit ball in octant 5. Inside the unit ball, or on it, so portion of unit ball, closed ball, in octant 5, and if you want to be pedantic about this, technically octant 5 doesn't include the coordinate planes, so you include the boundaries that are on the coordinate planes. All right, now it looks like this. It's just below octant 1, right? And it goes down here. It's 1/8 of the unit ball. It's just down below the xy plane, and within the unit ball, below quadrant 1 in the xy plane, the portion of the unit ball there. 1/8 of the unit ball. Yeah. So those are kind of tricky. You have to think about what does it mean for theta to be a constant, it's a half plane. What does it mean for phi to be a constant? In general, it's a half cone, but this particular one at pi over 2 is a plane. And then what does it mean for rho to be a constant? It's a sphere, and so if you put rho less than or equal to number, it's a sphere with its interior. Tricky, but it gets used to visualizing, which is important. Okay, what's good for today? So leave that up there for a second. I should leave it open. We'll do the next problem, huh? If you're online and take your mic off for a second, and you might be able to speak and put it back on. I think you have a question. Are you good at planes? I have a bunch of plane questions there. Plane determined by 3 points. What is it? Sketch a plane in the first quadrant, or find the equation of a plane that passes through a point parallel to another plane, or something like that.
NC or 2D.
Okay. Suppose I give you this one then, 10C. Write an equation for the set of points in cylindrical coordinates. Cylindrical coordinates, that's r theta z. rewrite the solution 4x squared minus 4y squared minus z squared equals 1. What kind of figure is that, by the way? And I asked you that question.
Okay,
It's plus and between x and
Oh, what is that? Sorry. Thank you. What kind of figure would that be? Just for fun, this isn't part of the question. This is actually a hyperbola in one sheet, right? You can write this as x squared over a half squared plus y squared over a half squared minus z squared over 1 squared equals 1. You take the ellipsoid with all pluses and change it to 1 minus, it's a hyperbola of 1 sheet. You change 2 minuses, it's a hyperbola of 2 sheets. Remember that? So this is just a hyperbola of 1 sheet from those 6 equations we remember for quadratic surfaces. One of our quadratic surfaces, these quadratic surfaces can often be written in very convenient ways if they're centered at the origin, in cylindrical or spherical coordinates, and that's what this will show. Now there's 2 sets of equations. The first one you can do, and this always works, is to put x equals r cosine theta, y equals r sine theta, and z equals z. That's the transformation. So if I give you an x, y, z coordinates, you can just substitute those in and it always works. However, I'm going to point out that sometimes it's more convenient to use these other equations. R is the square root of x squared plus y squared. Tangent theta equals y over x, and z equals z. If you happen to see tangent theta or x squared plus y squared, these can be easier. These normally just translate from, z equals z. What happens always when I try to write and talk, I write something strange. One time I was grading one of my students' exams and I got tired and I wrote on there, no Mardi Gras this year. I never figured out why I wrote that. I've never been to a Mardi Gras, but I wrote it anyway. I have no clue where that came from. But that happens on the board. All right. There's equally great stories about great mathematicians, so I feel in good company. So they say Newton was doing something and he was on his horse and he had to get off his horse to go up a hill. And so he dismounted, he walked up the hill, concentrating deeply. I mean, he's one of the 3 greatest mathematicians of all time, they say. And he got to the hill and his horse was gone. It was clear on the other hill. He didn't even notice because he was thinking so, concentrating so hard. And so I'm in good company if I do that a little bit. All right. So here's the point, is I could substitute r cosine thing and get r squared cosine squared and get r squared sine squared here. And then you have to use that identity, sine squared plus cosine squared equals 1 to reduce it. Easier, let's do this. Whenever we see an x squared plus y squared, like we can factor it out here, let's replace it just with r squared from this one, right? We memorize from this that r squared equals x squared plus y squared, just like polar coordinates. And so we can rewrite this as 4r squared minus z squared equals 1. Isn't that easy? So it's just one step there, really, or 2 if you count the factoring. There it is in cylindrical coordinates, just like that. Or you can substitute from these ones if you prefer and do the extra steps with trig identities. I want to look at 9C briefly because I think there wasn't actually any like that in the web assign. And this is one of the things I want you to learn out of this. I think that's why it's important to come to class and not just do the homework. There's so many little things I picked up later that I absolutely needed. So many proofs I saw in class that later, the only reason I understood something was I remembered how it worked because I saw the proof. And it's amazing how much that comes back and is useful later. So here's 9C. So where did it go? Yeah, 9C. It says, find the foci and asymptotes of the hyperbola 4x squared minus 3y squared plus 8x plus 30y equals 215. Oops, I'm drawing a projector here. How can I find those? the trick is to remember that all these things that have nothing more than squares, and you can actually have cross products x times y too, but you have to do a rotation first, which we haven't learned how to do. If you have nothing more than squares, then you can complete the square and recognize either a quadratic surface or a degenerate case or no solution. So let's complete the square now that we know that. This is what you get from class we didn't get in WebAssign. In each variable. So I take all the terms with x in them and I factor out the coefficient of x squared. 4x squared plus 2x, plus 4 times 2x. And then I take out the y terms, minus 3 times, or plus, let's put minus 3 times y squared. So I'll factor out the coefficient of y squared and collect all the y terms in here. And then minus 10y. And so minus 3 times minus 10y gives 30y, that one. And now I've got the x squared and y squared. I get all this equals 215. So I'll factor all the x terms out with the coefficient of x squared, factor out all the y terms with the coefficient of y squared. And now I can complete the square in each, right? All I'm doing is algebra here so far. How do I complete the square here? Plus what makes a perfect square? I take 1/2 of 2 and I square it, right? So I go 1/2 of 2, square the result is 1. So I need plus 1 here. And then over here, minus 3 times y squared minus 10y. What do I need to complete the square here? Half of 10, half of minus 10 is minus 5. Squared is 25, so I need 25 here, right? And now I've got that. But now let's see, I've added 4 here. And I've subtracted 75 here, all right? So I've subtracted 71. I have to subtract 71 on the other side too. So equals 215 minus 71, and that balances the equation. I subtracted 71 from each side. Yeah. So what do I have then? I have 4 times, right, the square that this is, x plus 1 squared. Minus 3 times y minus 5 squared is what that is, equals, and I've got to do the subtraction, 144. When it comes out of square, you know you're on the right track. All right, and now I'll divide this through by 144 to recognize the standard equation for a hyperbola. If I divide this by 144, let's see, it's x plus 1 squared over 36. If I divide this by 144, right, then I've got divided by 48. Y minus 5 squared over 48 equals 1. Oh, that looks like something I've seen before, right? This is, let's write it suggestively, x minus a minus 1 squared over 6 squared minus y minus 5 squared over, well, 48 is 16 times 3, so this is 4 square root of 3 squared equals 1. And there is the standard equation for a hyperbola that's been translated to have center at whatever is subtracted here. So this has center minus 1, 5, the numbers that are subtracted. And it has a equals 6. Here on the hyperbola, a is not necessarily the bigger number. It's the number under the it's the number that's squared under the positive term. So a equals 6, and b equals 4 square root of 3. So a doesn't have to be bigger than b in the hyperbola. In the hyperbola, you just put a under x and b under y. Unlike the ellipse, where they put a under, they just say a is the bigger number, whether it's under x and y. So there's a few twists here that make it kind of tricky. But there's the a and b. And then the question on there is find the foci and asymptotes. Well, the asymptotes would normally be y equals plus or minus b over a times x, right? What is it now? Well, I've translated. When I translate the center of the hyperbola, I also have to translate the center of the ellipse. So it's y minus 5 equals b over a times x minus a minus 1 is plus 1. where B is this one and A is this one. So it's y minus 5 equals plus or minus B over A would be 4 square root of 3 over 6. It's like, what, 2 square root of 3 over 3 times x plus 1. There's the asymptotes. You just have to translate them to max the center of the hyperbola. Now, how about the foci? You have to calculate C for hyperbola. C squared equals A squared plus B squared. So C equals square root of 6 squared, this time plus 4 square root of 3 squared. Well, this is the square root of 36 plus 48. Square root of 84. Let's see. So it's 21. Yeah, it's 2 square root of 21. Which means that the foci, since this opens with x, the positive term that opens in the x direction, you can sketch it if you want. The foci are this many units each side left and right of the center. So the foci are at -1 plus or minus 2 square root 21, 5. You just take the center plus or minus the focal length. And I suppose I should check that. There's a lot of complicated stuff there. I'll probably make mistakes in there, but that's the basic idea. It's time to go. Please check it. Oh, good, I got it right. There's nothing like getting it wrong right at the class time runs out. There it is. Try some other ones and come see me on Zoom or send me an email. And I can try to answer questions too. Good luck on Monday. Don't show up here, okay?